Our next presenter will be Joel Esposito from the University of Maryland. Please join me in welcoming Joe. Different affiliation.
Yeah, it's okay. Happens all the time. Joel Esposito from the United States Naval Academy. That's the undergraduate sister institution for the postgraduate school. Also in Maryland, but not University of. So first let me say I'm not a machine learning person, but this is joint work that came out of my sabbatical at Columbia University's Data Science Institute and trying to take a look at how some of those techniques might be applied in robotics. So my story starts with going to a talk in about 2013 on something called pixel inpainting. And what you see in those kind of talks, if you're not familiar with it, is a lot of pictures like this. So this here is a picture, a digital image where something like only 20% of the pixels have been observed directly. And then the challenge there is to try to see if you can recover the image from that. And for those of you who use MATLAB and work in computer vision, maybe you can guess what the image is, but the algorithms that do it don't use any prior knowledge or any database of images to match to. So if you know what the image is, raise your hand. Yeah. So, right, it's the cameraman image, of course, but I think that's easy for us if we've seen this image, right? So my first reaction when I saw this talk is, it's witchcraft. There's no way that that's possible, but of course, when you think about it a little bit, it makes some sense how that's possible. It's sort of the opposite of what happens with image compression. And of course, my second thought was, well, how can we use this in robotics? So the first question you have to ask yourself is when can we do this, right? When is this kind of thing possible? So the assumption or the structure in these problems that gets exploited here is that the matrix, the image in the previous slide, but in general it could be any matrix. It can't be an arbitrary matrix. It has to have some structure, and the structure we're looking for is a matrix that can be separated into a low rank component and a sparse component. So the original matrix is expressed as the sum of these two. And then when that's the case, there's some technical conditions on the sparsity and the rank. And if you have enough samples, you can recover the low rank part of the matrix with high probability. So this has been done in a lot of other applications. Probably the most famous one would be in recommender systems. You can think about what Netflix does, right? There's this giant table, this giant matrix, and each column represents a movie title, and each row represents a user, someone who watches those movies. And very few people bother to rank the movies. Maybe something on the order of 1% of people or less put in a rating for movies. But you still want to use that information to predict what movies someone might like so you can recommend better films for them to watch. So it's the same idea in a whole bunch of other applications there. So I want to see if I can do this for motion planning. So this is the application I'm thinking about. If you know much about probabilistic roadmaps, the idea is that we have some environment here, and this is a very simple 2D environment, but it could be very complicated. And we generate a whole bunch of samples in the configuration space. Those are the blue dots. And we collision check some of the edges between those, and we find that some of them are valid paths, and we also find some of them might not be. And I never really thought about it this way, but if you think about the adjacency matrix that goes with that, each time you check an edge here, you're filling in an entry in the matrix, and there's all these unknown entries there. And often that's just where we stop. But my question is, can we take what's here with no additional collision checks and recover all these question mark entries here? Right? And there may be many, many, many of them, especially when the matrix is large. So in order to answer that, the first thing we have to ask is, do our problems fit this model? Are they of this low rank plus sparse structure? And I think the answer is yes, at least for the problems I checked, and I'll argue why. But we computed the low rank plus sparse decomposition for that environment you saw on the previous page, and what we can separate it into, that adjacency matrix becomes the sum of a rank 2 matrix, and each component of that matrix represents one large convex cell in the workspace. And then the sparse component can be interpreted in this way. Most of the entries are 0 because it's sparse, but the ones that are 1 can be thought of as connections that happen between these cells, right? And that provides the connectivity, and you need that to solve the planning problem. And the negative entries are corrections to this low rank structure. So there's a small protrusion there that we kind of overgeneralized and filled in, and we need to remove those, and that's what the negative part of the sparse matrix does. So in our experience, in the examples that we've tried, this structure is held for these problems. Of course, not all this simple, but this is nice because you can show it in a slide. And we conjecture that for many practical examples in motion planning, they're going to possess this structure in the same way that people have conjectured that in many practical examples, the expansiveness or the goodness of the workspace is there. To see why that happens, I think it's pretty intuitive. Of course, it took me like a year to see this, but if you take the adjacency matrix and you throw out the convention that we put zeros usually on the diagonal, if you put ones on the diagonal and you permute the entries, you see there's going to be this block diagonal structure with these little corruptions that represent the edges that get corrected there. So that's the intuition behind why this works, and it works on fairly large examples. So here's an example from the open motion planning problem. There's a small L-shaped object. You have to fit it through this narrow passage. If you just look at the raw adjacency matrix, it looks something like this. It's very hard to discern any structure from that. If you compute the decomposition, what you see right away is that there's really 3 regions of interest in the workspace. 2 of them are really large, right? And they correspond to the left and right blocks. And there's a smaller, more complicated structure that probably corresponds to going through the hole there. And the sparsity pattern tells you where this is not quite true, right? So probably there's a lot of configurations with the L-shaped object when it's almost in contact with the walls, kind of breaks this block up, and that's what a lot of these are about. And there's a lot of scenarios here where you can fit through that, and that's what the white samples in the lower right corner are all about. Okay, so now on to the main question. The main question is, what if we don't know a lot of the entries? How can we recover them? So this is what our matrix looks like. Our algorithm looks like. We first generate n samples in C-free, so nothing different there than standard sample-based motion planning. Then we collision check some fraction of the possible edges. You can use different heuristics to do that. We sample the edges at random. We kind of vary the fraction, and I'll talk more about that later. So we get this more minimalistic graph there. And then this is really the main part here. We have to solve this convex optimization problem. So the problem is that minimizing the rank isn't convex, it's NP hard, and minimizing the sparsity isn't convex, it's NP hard. So we use convex relaxations of that, and that's a standard technique in this community. So the nuclear norm, my laser pointer died, but that's the norm with the star. That's the sum of the singular values. That's a proxy for rank. And then the L1 norm, that's just the sum of the L1 norms of the entries in the matrix. That's a proxy for sparsity. The objective is some weighted combination of them. We have some constraints in place. The first one means that the sum has to match on the observed entries. So anything that we collision check directly, the final matrix has to respect that. And then we can't encode the fact that this matrix has to be a binary matrix, ones and zeros. That can't be encoded as a convex constraint. So we have some extra constraints that help with that bound the entries. And the theorem from this literature is that if we check, directly observe n log n squared entries, edges in there, we're going to be able to recover the low rank component with high probability. So that's exactly what we do. And let me talk a little bit about the quality of the solution. So we recover many, many, many edges that were not directly checked. So I'll give you a sense of the magnitude of that. Something like from 4% of the edges that we check, we can recover like 93% of the status of the unknown edges. But there are some problems. There's some false positives and false negatives. The false negatives are not a big concern because we live with those all the time in motion planning. So that means that we did not infer an edge where one really exists. And that's fine. So we may miss a short path there. And that's what the red line on the right shows, right? There's kind of a short path through the gap, and we don't pick that up, and that's fine. But there are also false positives, and those might be a cause for concern. So on the right panel, on the lower side, you see that we picked up an edge that goes right through that protrusion, which isn't really there in practice. So the false positives are bad. The false negatives aren't a big deal. When I talk about the error rate, I'm going to focus on the false positive rate. But there are a couple other interesting properties here. One is that because of the constraints, the completed graph inherits some nice properties of the original graph. So if your original graph is connected, the completed graph is going to be connected as well. If your original graph is accessible, which just means from any point in the workspace you can jump onto that roadmap, we're going to inherit that also in the completed graph because it's the same vertex set. More interestingly maybe is that the path lengths are no longer and they're usually shorter. So we pick up a lot of these long edges here, a lot of these shortcuts that we wouldn't directly collision check, probably pretty expensive to collision check, but a lot of those come up in the complete graph. So in general, the path lengths are much, much, much shorter. This slide puts in perspective sort of the numbers for how well it works and not the qualitative properties. So this is a common depiction in this community. They call this a transition plot, and it shows on the x-axis how many entries were sampled. And on the y-axis, it shows you the number of errors. So the blue line is the actual number of errors, that's edges that we incorrectly estimated. The red line is the false positives, and that's what's really bad. So what you see here is, in this particular example, and I should say Mark Mull and Lydia Kravacki were really generous in sharing a lot of data with us that they generated with the Open Motion Planning Library. So a lot of the examples come from that. But what we see here is that after we've collision checked something like 4 or 5% of the entries, of the edges, we can correctly recover something on the order of 95% of the remaining edges. And there's something like 2 to 3% false positives. It still might be a lot of false positives, but in some ways it amazed me that there's that much information in the samples there that you can recover that many entries. So we're recovering something like 92% of the 125,000 entries there without any additional collision checks. So just from the structure of the problem, we have this. This pattern is pretty typical there. With low sample values, there's very little completion, very little extrapolation. Then there's a transition region, and then there's the steady state region, and that's what the green region is on the right. So once you pass some threshold, there's the sharp transition, and you're recovering the low rank part. And all the errors come from the fact that if we don't sample the sparse terms directly, there's no way that we can infer them, right? So it's not magic. There's something there that you have to measure. That's what makes the sparse term sparse. Okay, so now for the dirty laundry slide. I think dirty laundry comes on a continuum, and it ranges from, the pair of jeans that you wore and you're like, yeah, I probably could wear them again. Maybe I'll do the smell test. Down to the clothes that maybe you wash, and even after you wash, you decide to throw out, right? So I don't know where all this falls on this. So I think one issue is, do we even want dense graphs? And that's a really valid question, right? There's something to be said. In fact, in a lot of planning algorithms, there's steps to prune the graph so that you don't have to search and store a very large graph. So I fully admit that. But there are other applications in which you want to have a dense graph if you really care about short paths. We saw a really nice talk on dynamic replanning in the cloud the other day. And in those scenarios, I think you want that. So I think in the right application that works. The sample complexity is another issue. So the results from that literature, the motion planning literature, suggest that that number of samples would be right, but probably we could do better. The last issue is the false positives, and I don't know that there's an easy way to get around that. There's some things we could do to bias the objective function and kind of discourage those from happening. But the bottom line is if we don't sample those entries, there's not a lot we can do to recover. So I'll end on that note, but I think more than this algorithm having some huge practical utility there, I think it's really interesting what it says about the motion planning problem. It says that there's a lot of information we have there that maybe we're not using that can be used to recover a lot of the structure of the problem. And I'm curious to see what anybody else thinks about what other problems in robotics maybe can be solved with these techniques. So I'll stop there. Thanks for your time.
Thank you. For questions, let's start with the respondent here, David Rosen, and then we can go to Mark after that.
Hi, so thanks. This was a great talk. I really think it's a very cool insight into this problem function that might not have been obvious. Thanks. So my question then would be, how sensitive do you think your technique would be to the notion of connectivity that is used to generate these graphs that you then recover this low rank structure from? And sort of as a corollary, how do you think this might generalize to environments that have more clutter in them than maybe some of the examples that you considered in your talk?
Yeah, good question. Thanks. In general, the clutter is probably modeled by the sparse terms, right? So the more clutter you have, the more sparse terms there are there. And at some point, the whole matrix, if you have enough sparse terms, it's not sparse anymore, right? And the method breaks down by that, right? So yeah, there are some technical conditions on how sparse it has to be, and I think an area of future work is probably to relate those to real geometric descriptions of objects in C space. Thanks.
So, I don't know, are you familiar with the work from Dinesh Manocha and Yapen on probabilistic collision checking?
I'm not.
Oh, well, I was wondering if you had thought about maybe with a probabilistic interpretation of the matrix that you're completing, that you can sort of, for the edges that you're predicting, you start assigning some probability of how likely it is that they are collision-free or in collision.
Yeah, that's a really good insight. That was something that we've been looking at. If you recall from the algorithm, the very last step of the algorithm is to round all the entries, right? Because there's no way in the convex program to force the entries to be 1 or 0. My intuition tells me that if you don't round the entries there, they somehow relate to the probability that that edge really exists, right? I can't prove that, but I can construct some real simple examples by hand with 3 and 4 vertices that suggest that's probably the case. So I think I'm probably leaving some information on the table by rounding the entries and not using what's there.
So is there, maybe this is a bit naive, but is there any reason you can't just use the entries in the sparse matrix as a set to actively test collision with, so that you can sort of as a selection for this is the ones that we are somehow uncertain about or need to check more on, rather than trying to just round them, it's a much smaller set to check, making your collision check much cheaper than trying to check all pairwise examples.
Yeah, that's a great example. The problem is that the sparse entries are always right. You know, you can, if you look really carefully at the objective function, the way that it's set up is that the sparse term is really there to capture the constraints, to capture the fact that if you've observed an edge, it has to be in the final matrix. So the false positives come from the low rank part, which usually is not sparse. So probably checking all those, you know, directly probably wouldn't save us a lot of effort. So one of the things that my co-author suggested, and he's not a roboticist, was he said, okay, well, you solve this, and then you try to find your path, you do graph search, and just before you execute it, you just collision check all those edges. And it seems like a reasonable thing to do in practice, but it'd be nice if we had a bound for, you know, how many times you might have to do that before you found a valid path.
Jane, could you come and set up? Time for one more question.
Yeah, that's a good question. So, you know, the crude answer is for these examples, it, you know, is on the order of minutes. So 3, 4, 5, 6 minutes like that. Of course, these are kind of small examples, but I also would say that our implementation's definitely not as tight as it could be. The cost of the algorithm is really dominated by computing singular value decomposition. So if you have a really good method to do that, then it's going to be relatively fast. That's the dominant cost at each iteration. And usually it's on the order of 100 iterations.
Thank you.
Thanks.